Okay, good morning, everyone. Welcome to the 9th GSA Annual Graduate Student Research Day. My name is Zhou He. I'm the president of GSA and also the chair of the Research Day Committee committee. I would like to welcome you to this great event because we have been preparing for this for over 1 month. And with the preparation, I feel like it's a great honor to be here and to be in part of this kind of big party. And last year, as you have known, we had gone through a really difficult time because of the unprecedented Sandy storm. And this year, we got an unprecedented success due to our efforts. We have got over 80 submissions, and after the deliberation of the committee members, we got over 70 posters accepted. So today, 11 departments gonna present their poster in the form of posters, and also we're gonna have 6 posters from Rutgers University. It's gonna be a great success. I'm looking forward to the event today. First of all, let me first introduce the agenda of the day. From 10 o'clock to 10:15, we're gonna have the welcome remarks, and from 10:15 to 10:30, we're gonna have the keynote. At 11:30, we're gonna have the keynote address, and from 11:30 to 12, we have a coffee break, and after 12, we're gonna have 2.5 hours for poster presentations, where the posters are gonna be judged by the professors in NJIT. And at 2:30, we'll have the award ceremony. So first of all, please let me welcome our president, Dr. Bloom, to give us some welcome remarks.
Good morning, and welcome to the 9th annual GSA graduate poster session. And first of all, let me start by thanking the GSA, our Associate Provost for Research, our Provost, invited guest speaker, and to all of you who are doing the research. And when you get to go from event to event here on campus, you have some time occasionally to reflect and think about, so we do research here, and what exactly is the research that we're doing? And to reflect on the definition or our assumptions about research. So one of the things that I recall from many decades ago, one of the first person who introduced me to research said it's a creative process. And I never envisioned research as being a creative process. But as I'm sure some of you are engaged in this and you realize, it's a very creative process. And a creative process is one of those higher order thinking skills that many of you are somewhat gifted with, and therefore you're able to do research. The other thing I would say about a creative process is it takes time, which is why for those of you who are Ph.D. students, for example, you find it's a process of a proposal, it's a process of finding a research methodology, finding an advisor, putting a team together who's going to review your work, and then all the years that you put into the research. Because creativity, unlike some forms of creativity, the kind of scientific research is not like possibly some artistic forms of research. Even there, it takes years to develop artistic talent, to dance, to paint. So it is a time-consuming process for which we thank you for that. The other thing about being creative is usually it works better in teams. Teams of people push one another. They challenge one another, assumptions that people have. And they ask you to read sometimes, I'll never forget, having nothing to do with most of the research going on here. I was doing research in the area of economics. And they told me to read about evolution. One of my faculty members did on my team, to read Darwin on evolution. I said, what does evolution have to do with economics? After I finished reading Charles Darwin, which I never would have, nor did I ever think about reading, I realized the relationship. I won't walk you through my dissertation now, but there is a relationship between evolution and economics. So it's a creative process, it's a team. And then, and I thank you for the posters that you're presenting here, you expose your creative process, you expose the work that you do, and you ask others to judge it. This is very, very hard work. It's creative, it's time-consuming, it takes a team, and all of that results in some very hard work. But it often results in one of three things. You're advancing a body of knowledge, you're contributing to the knowledge, you're possibly even contributing to the solution of a problem, and what many of you are about these days is finding another application for that knowledge. So think about the contributions that you're making as a result of working with a team, being creative, and doing the hard work. I thank you, and I wish you good luck.
So next up, may I invite our provost, Dr. Dick, to come up to give more welcome remarks. Thank you.
Thank you very much, Z. Good morning, everyone. It's a pleasure for me to be at this event. In fact, this is the very first event for me with the graduate students since I've become provost. I wish to begin by thanking our president for being here in support of this event, and also thanking the Graduate Student Association with all its officers for the marvelous job that they have done here, and they have done consistently. They have shown responsibility. They have shown the ability to organize a significant event all on their own. As you all know, this is all conceived of by and constructed and run by our students who fully understand that there is no separation between education and research, that without the students, without the graduate students and their work, there would not be a research university, and certainly without the research university, there would not be graduate students in graduate programs. I was impressed by the long list of projects that are being shown here today, and the projects that will be presented. I was commenting to Sotiri regarding the quality of the work that is being done with me as a computer scientist. Of course, I was immediately drawn to that page from the College of Computing Sciences. I've been disconnected somewhat from the work that has taken place there since I moved out of computing sciences a little over 10 years ago. But also, I stumbled on one project that is from a totally different area that I'm familiar with, and that is in biomedical engineering in collaboration with Rutgers University and the medical school. I had been interacting with that student for some time over email, whose own research interest overlaps somewhat with mine, who took time to learn about my work and wanted to examine how my interest in learning systems and software underlying such systems can come together with his own interest in learning systems and hardware. I, of course, want to acknowledge the presence of Dr. Markus Hofmann from Bell Labs, who is our keynote speaker, and all the faculty that serve as your advisors. As you know, this is not an easy process. Dr. Bloom talked about the creative process, the efforts and the time that go into it, and that is both on the part of the student as well as on the part of the advisors. Being a current and a former advisor myself of Ph.D. students and graduate students, I know the relationship that develops between these two entities, the student and the advisor. I'm very familiar with it, and I can imagine the work that goes into it for projects such as yours. So I am so happy to be part of this event this morning, and I am so grateful that our own Graduate Student Association is mature, is responsible, has the foresight to, in fact, put such a program together. And I thank every one of you for their participation, including those who have helped in organizing this event and make it the successful event that it is today. Thank you very much.
So next up, may I welcome and invite our interim associate provost for graduate study, Dr. Ziavras, to introduce the keynote speaker for today. Thank you.
Of course, after what our president and provost said, there are not a lot of things that I can say. But first of all, I want to congratulate Zhou He, who did an outstanding job. I'm the advisor to GSA, and they are unbelievable. You know, they are very active. They organize lots of events. This, of course, is a very, very important event because students showcase their research. And of course, we have to congratulate the advisors as well, as Dr. Dick told us. So, Zhou He, congratulations. I am honored to introduce our speaker, Dr. Markus Hofmann, who joined Bell Labs in 1998 as a researcher. Then he moved into a project manager position, and finally he became head of Bell Labs, which is part, of course, of Alcatel-Lucent, and has a lot of reputation for introducing many innovations to the world, like UNIX, DSL, C, C++, lasers, and MIMO in communications, and so on. He has overseen research primarily in the areas of multimedia communications, optics, wireless communications, cloud computing, internet, content networking, and some more areas. But he has primarily contributed in terms of reliable multicasting over the internet, defining and shaping several fundamental principles in relation to content networking. And currently, he is the leader, worldwide leader for Alcatel-Lucent, with respect to the production of new IP platforms with emphasis on systems and software. He has published very extensively. He has more than 60 journal and conference publications, and he has 14 patents already issued. He received his Ph.D. with honors from the University of Karlsruhe in Germany. And his talk is, of course, about industrial research. So welcome to NJIT, and thank you for being here.
Thank you very much for the introduction. Thank you very much for having me here today. It's a great... This one, yeah? Better? Okay. Thank you. It's a great pleasure being here. Not just because I like getting out of my office every now and then, walk on the campus and feel young again, but also because I love research. And what I want to do is to talk a little bit about research, in particular research in an industrial context. And talking about love, and to get the juices flowing a little bit, let me ask, who of you in this room loves problems? Raise your hand. Who loves problems? All right, so that's not even half. And that's a little bit surprising, because we are in a research organization, and research is all about solving problems. So I would expect that you all love problems, that you all love running across problems, embrace them and solve them. And this is really at the heart of research. Research is a problem-driven, and at least in the industrial context, a problem-driven kind of initiative here. We are here to identify what are the challenges, the problems we need to solve, and then we come up with solutions. We then come up with the solution that will solve those problems. We come up with the how. This is actually also what we do at the colleges, at the universities, right? When you are, I don't know, sitting in the study room and mulling over the questions in the exam, you are being asked how to solve certain problems. When you write your master thesis or your seminar work, you're looking into how you solve a specific problem. And this is how we are being trained. But let me tell you one thing, the how is only table stakes. It's the simple thing of research. It's the easiest thing of research. Finding the solution is easy. The hard part is finding the problem. And this is something that I believe we, during our education, are falling short a little bit. We are so focused so much on the how. We always forget that we also need to train ourselves finding the what, and in particular the why. These are the big questions for research. First, we do not start with the solution. That's a common mistake we all make in research. We start with the solution and then try to construct a problem around the solution. Wrong. Very wrong. In particular in industrial research, what we have to do is start first with the why. That's the opposite of what we do in many cases. As researchers, we often look at the how, then try to find the problem. Wrong. First, identify the problem you want to solve. Ask, why do I want to solve the problem? Why is it relevant? Who would care if I solve the problem? If nobody cares, you're wasting your time. Find the problem, then define what do I need to do to solve the problem, what are the different steps, and then you look at the how. Right? That's the easy part. You're all smart. You will all figure out the how, believe me. Finding the problem is the tough part. And so I've been with Bell Labs now for 15 years, and I went through, again, I started as a researcher all the way to heading Bell Labs research globally wide. So I went through it myself many, many times. Finding the problem was always the toughest part for me. That's what I was struggling. I want to share a little bit with you some of the examples so that you know what I'm talking about, and maybe we can see that using some of the examples. Let me go a long time back, 15 years, when I was still a student, right, and I was working on my PhD thesis. I was working on multicasting. Multitasking meaning how do I transmit data from one source to a very large number of people. Right? And I got interested because it's a very interesting, challenging area. A lot of challenges, a lot of math to do, communications, protocols was a great area. I just got excited about some of the ideas I had and developed a whole system on how to transmit data from one source to a large number of users across the globe. The problem was I hadn't thought about the problem I want to solve. So then I developed all these technologies and all the ideas, how to do multicasting efficiently and at low cost and with ease and simplicity. And then I thought about, okay, what problem do I solve? Well, then if you think about it, one problem you could think about is, okay, I want to get data from one source to a large number of people. That's content distribution, basically, right? Okay, let me deliver videos to people. Let me deliver, I don't know, photos of people or whatever. So that was my use case. That was my problem, all right? But for all of you who are in telecommunications and in networking, you know that multicast did not take off for many, many years. And even today, looks totally different from what at least I had envisioned. So I consider that work actually a failure, to be honest, because I did not solve a real problem. Now, it got me a job at Bell Labs, so it was great for me, right? But it did not solve a problem. When I actually joined Bell Labs at that point, and I joined through the multicast work, I thought about that, and I was not happy. I wasn't satisfied. I had a great time. I enjoyed that work a lot. I had met great colleagues. I got my PhD out of that. I got a job at Bell Labs, but I wasn't satisfied. Why? Because my solution was not in the real life. Nobody was using it, other than academia. That's not why I want to do research. Then I went back and said, well, let's think about the problem that I thought I solved. I thought about I'm solving a content distribution problem, all right? Then I thought about it, okay, let's forget everything I liked on the solution multicast that I work on. Let's think about the problem first. Let's not start with the solution, let's start with the problem. So then I started thinking about, okay, if the problem is to deliver content to a large number of users, are there other ways? And then this is how we got into the content delivery and web caching, streaming caching world, where we then started defining global content delivery networks that at some parts might use multicast, but use a lot of web caching technology, streaming caching, global load balancing, if you know about Akamai, these kinds of solutions. Right, and we came to that because we looked at the problem first. We didn't start with the solution, we looked at the problem. Problem, deliver content from one user to others, what's the best solution, right? And then we came up with a different one, not with multicast, but with a caching-based solution. Right? So this is what we developed, and actually that's the next lesson learned from my work there on content networking. So we again worked then very closely with some of our big customers and see what's relevant, what can we roll out, and so on. What do we need to focus on? And this was already good because we got much more insight into what's actually needed in the field. And that was also the time that was around 98, 99, 2000, right, with the dot-com bubble, where a lot of activity was going on. And even research itself, the research community picked up on that space. And there was a lot of work, and interesting, exciting conference papers written, tons of them, about cache replacement schemes. So cache replacement scheme, just for the folks who are not in that area, means if I basically have a system and I want to store content on that system, on the disk, but my disk is full, I need to decide which content that I have stored on the disk I eject, so to make room for the piece coming in, right? So that's cache replacement. And there has been tremendous amount of papers working on all kinds of sophisticated cache replacement schemes, really clever work. A lot of math, fantastic, outstanding, high quality work. Tons of papers. I reviewed on panel, I don't know how many papers on the topic. But to be honest, they all missed totally the mark. Why? Because the price for hard disks was dropping to almost zero. So nobody cared if I come up with a cache replacement algorithm that is 2% more efficient than the other one. Because 2% is nothing in cost, I just buy a bigger disk. Nobody cared. In particular, nobody cared because all these clever schemes were so complex that they were hard to debug, hard to implement, hard to maintain and to control. So what caching schemes do we use today? The simplest one you can think about, LRU and LFU, least frequently used, least recently used. These are the caching schemes we still have in place today. Slight variations, but that's basically it. Why? They are simple, they are easy to implement, easy to understand, and they are good enough because the prices for hard disk fell so much that I don't have to worry about squeezing the last little thing out of the hard disk. That's another example, and I have to admit, guilty as charged. I wrote myself 2 papers about great cache replacement algorithms, right? But again, I have to admit I missed the mark. Why? Because I did not understand the problem. I did not understand that saving a little bit on hard disk was not a problem at all. My customers looked at me and said, Markus, you're solving a problem that's not irrelevant for us. I don't care. I put $10 more in the hard disk and problem solved. Right? So again, we have to ask, what is the problem? And is it relevant? Is it relevant? I always have 5 questions that I ask my teams. So everybody who comes to me and presents a proposal, I ask 5 questions. And I hope that if you wake up one of my researchers at midnight and ask for the 5 questions, within 10 seconds you should have them. Because I keep them repeating again and again. First question, no surprise. What is the problem you want to solve? Second question, why is it relevant? Who cares if you solve the problem? If there's nobody out there who cares if you solve the problem, you're wasting your time. Right? Third, very important also, convince me that the problem is not yet solved. Convince me it's not yet solved. That's very important. You might laugh, but you won't believe how often I have researchers coming into my office and then pitching an idea to me, and then I turn around and ask, have you looked at this startup company? Have you read this research paper? Have you bought that product? They solve the problem you try to convince me is important. So you know the state of the art and know exactly why the problem is not solved yet today. That's the third question. Right? Then the fourth question is, well, we are all researchers. We all believe, and in most cases rightfully so, that you're pretty smart. So at Bell Labs, I push the threshold very, very high. So I don't want to waste our time in solving trivial problems. It might be, again, might be a problem, might be relevant, might not be solved, but if this is something that, I don't know, somebody can solve in 2 weekends in their garage, I'm not interested. Because I'm wasting my time, because I will not win that fight. I want to know, that's my fourth question, why is this a hard and tough problem to solve? There might be different reasons, right? So now you established after those 4 questions, you almost scared me. You said that's a huge problem, that's relevant, a lot of people care, it's not solved, and it's almost impossible to solve, right? And now I'm totally unfair to ask you, okay, now you have to convince me how you will succeed. Okay? And then you have to tell me that you have something that nobody else has that makes you believe that you succeed. Once you answer all 5 questions, then I start talking. If you fall short in any one of those, I'm not interested. All right, so this is the 5 questions that my team has to answer every time we talk about things. And so this is how we do it. Now, I have to admit, it sounds harsh, and I probably would fall short on any attempt I make in explaining that, right? So I have to be really honest here. But it's a good exercise. Think about those questions when you put a proposal together. Think it through, and this will help you guide a lot, all right? Let me use another example about an interesting one, that actually was totally surprising to me. Who knows what that is? I actually have one of those here. You know all these big, nasty cell towers that make our cell phones work? That's a fully functional cell tower in that form factor. We call that a cube, a light radio cube. This was all triggered by the idea that it was all basically we need to improve the capacity on the networks, and with the macro cell architecture we have, you can't do that. We need to move towards small cells, femtocells, macro cells. But if you do that, you also don't want to have these huge, ugly antennas that require a lot of energy, are not nice to look at, have a lot of radiation that people are concerned about, and you can't cover the areas with the bandwidth you need. We need to move towards small cells, femtocells. But then you need to make these antennas, these space stations, smaller, right? And actually, the leader of our wireless research team, a couple of years ago, went down to his basement, into his wood shop, and created a wooden cube of that size, a wood cube. We actually still have the original wood cube in the labs. And he held that up, just like I'm holding up that, and he said, make this cell tower fit into this one here, get back to me in 6 months. And they did. They did. They came back with that. So that's really impressive. And by the way, this is like a Lego block. We can combine multiple of these devices. We can have arrays. We can create macro cells based on that, metro cells, small cells. You can mount them at lampposts. You can hide them behind walls and everything. So pretty neat thing. The reason why I'm bringing this here in the context of our talk is, as you can imagine, squeezing a cell tower into that form factor had a lot of challenges. We had to think about the antenna design. That's the antenna. And there are physical limitations how small you can make it, right? We had to think about integrating the boards here, the RF boards and the software functions in here. A huge problem was thermal management. These things dispose heat. And if you want to shrink that, you have to control that. And there was no way doing that in the old-fashioned style where you basically slap a heatsink on the back on this device. This does not work. We had to actually bring our groups who designed the RF boards, who designed the boards of this device, together with the guys who do the thermal, the physics, the thermal management. We locked them into a room and told them, don't come out before you have the problem solved. And by having those teams talk to each other, what they actually came up with is, it's wrong to do the board design and the heat management design separately. You have to integrate it. They basically built the board into the heatsink. And that way we're able to achieve that form factor, right? So all these things went here, and the focus was really in getting this thing so small, making it cost-effective, and actually high performance. But when you then start talking to our customers about that, there came one problem we had totally missed, they brought up, which changed the way the direction of our research. They basically said, Markus, this is pretty cool, this device, really. It's fantastic technology and really, really impressive. But you know what? What is the weight of this thing if I have an array? I first didn't get it, what they mean, weight, how heavy is it, why is that important? Well, they said, well, if you want to mount these things on lamp posts, weight is important because there's a certain maximum weight these things can have so that based on union and worker laws, the workers can still use a ladder to go up as opposed to a crane. A problem I had not thought of at all. But a real problem, a deployment, a killer. If we would not go beyond that weight limit, that means every time they want to mount one of these hundreds or thousands or millions of devices to a lamppost, they would have to roll out a truck. That would have been a killer, would have been the death of that technology, right? So therefore, we started worrying about weight, something we had not on our radar screen at all at the beginning, all right? So again, something that we missed the problem. Now, luckily, that was solved too, right? And luckily, because we have interactions early on with our customers and our BD partners, we learned about the problem, and it changed, to some extent, the direction of the research, right? Why? Because we asked what the problem is and then went after that problem, okay? Another nice example on how actually the problem can change how you approach the research. So what are the problems we still need to solve? That's also something I'm often asked, because if you just think about the advances that we had the last years, it's amazing, right? I don't know, the iPhone was introduced when? Now it's 7 years ago. 7 years ago, I had a flip phone that I used just to make calls. I could not even imagine how somebody would ever want to take photos or videos with a phone, or how I would read email on that thing 7 years ago. And now it has totally changed. I feel already nervous here because my iPhone is with my little son over there, right? And it's too far away. I get anxious if I don't have my iPhone with me. 7 years. That's tremendous. So what's left? Very often the question then is, Markus, what are the areas, the problems we still need to invent in? Is there anything left? You're challenging out what are the problems. So I don't have the answer. If I would have the answer, I would probably be a billionaire now sitting at the sunny beach, right? But I can try to help you a little bit how we approach that. So we, of course, talk a lot, and I admit that's a little bit an unfair advantage we have. We talk a lot to our customers, with media analysts, with our business divisions. So we get a lot of inspiration from that side. But there's one source of information that you never should underestimate, and it's yourself. So I look a lot at myself, at my family, and again, my little guy here, Kevin, can confirm that. We talk a lot at home about how is that iPod working out for you? How is the iPad working for you? How is the phone service? Do you like the video chat that we do with grandma across the ocean? How is that working out? And these are things that we use a lot. So for example, I mentioned before that I was starting to work at content networking when I joined Bell Labs. That was driven by the fact that I left my family behind in Europe, Germany, and all our 4 kids were born in the U.S., and my parents, their grandparents, was hard for them. They wanted to be part of their lives. So we started putting up a blog, sharing photos, videos, putting videos up, doing Skype calls and all these kinds of things, right? Which helps my parents to be part of their grandkids growing up on the other side of the Atlantic. But we are still not there. We're still not there. It still feels different if we sit, I don't know, over in front of the TV set or with a mobile phone and try to share photos or videos with them. It still is different if I click on a web link and it takes a few seconds for the video to start or for the photo to display. It still feels different than sitting next to each other and flipping through an album with photos. There is no delay in turning the page. Why do I have a 3-second delay to display the photo on the web? There's a different kind of intimacy here. If I'm sitting in the room, I can close the blinds and I'm alone. I can say and do whatever I want. Nobody will notice. Do I have the same if I do that over the internet? I don't know. I don't have that feeling. I do not have the feeling. I tell my kids, never ever put anything on the internet that you would not be fine for the entire world to see. Never ever do that. In my home, I can. I don't have that same feeling. And yes, it is true. We are actually on our way up to Lake Placid for the hockey tournament. And I will have my iPhone with me, and I will hold it up and do a FaceTime so that they can see when my little guy does the shootout later tomorrow. And my family, my grandparents, my parents across the ocean can be there live. But it is different. It still does not feel like that. And this is what I want. This is what I want. There's a lot of work to do on user interfaces, on communications technology, on security and privacy. Don't believe a second that we have solved those problems. We are just scratching the surface. We are just going there. Other example. We talk about me being in Lake Placid, holding up the iPhone and doing stuff. I want to communicate everywhere. Now, to be honest, if I'm at a beach like that, I don't want to work, right? So don't get me wrong. So I will not do that. But the idea is actually that, okay, I want to be able to communicate whenever I want, no matter where I am. And I have to be really honest, I have an office in Bell Labs, but I rarely use it because my office is where my tablet is, where my iPhone is, where it is. I take quite a few calls. I actually took business calls from the beach. I did that. I can do that because it was an audio call only. I couldn't do it yet with video, because nobody likes watching me in a bathing suit at the shore while talking business, right? So, however, we actually worked on technology that extracts the background from a video. We actually had a prototype running where I could sit at the beach, and we then using these blue screen, green screen kind of technologies, we put a business background in the screen. Now I had to put on a shirt for that, all right? But you could not realize that I was sitting at the beach. So in the future, it does not matter where you are. You can do business or communicate from wherever you are because we have the connectivity, thanks to things like these. But we also will have user interfaces. We need to get there. It is still not there, right? A big game changer was when we had mobile video on the smartphones. So I use Skype-like things for a long time since I came over. But, well, my kids never really understood why they have to come up to my little office to talk to their grandparents and we have to sit around a PC. They didn't care. But now I can take my smartphone, right, and I can chase after them as they are sledding down the hill, throwing snowballs, or being on the hockey rink. I can hold it up and then just show my parents live on the other side on the Atlantic. Big game changer. But we are still not there. We are still not fully there, all right? So we need to change that. So how do we get there? How do we get there? Well, the first thing is learn from experience. What I said was, okay, understand what you want to do, and then build the right vehicle for it, right? If you don't do it, that happens. You might build the best two-wheel cart that you can find. You might have the best donkey here, but if you don't build that vehicle for the purpose that people want to use it, it doesn't work, all right? So we have to learn from experience. We need to, A, make sure that we solve the right problem, that we understand the constraints that we have, and then actually develop the solution. So remember that guy, right? I hope you still do, right? That guy, the idea was, and this has been in the wireless communications world, has been for decades, we talked about everywhere coverage. That everywhere, we need global, ubiquitous coverage everywhere. And we have been rolling out these cell towers, and now with these devices, we even go in-building coverage and so on. So it has been long a mantra of the wireless communications technology, we need coverage everywhere. Do we really? Well, let's take a look at some data. This is data we took from some of our customers' networks. And it shows different wireless cell technologies here on the x-axis. And on the y-axis, it shows the percentage of the total network load. So for example, here you see that the top 32% of all wireless cells carry about 35% of the entire network traffic. Another number here, the top 10% of all cells carry half of the traffic. Half of the traffic is carried by only 10% of the cells. If I go up to the top 50 cells, half of the cells we have out there today carry 96% of the traffic. Half of the cells carry almost 100% of the traffic, meaning that the other half is basically sitting useless. So it is not about providing ubiquitous coverage everywhere. It is about providing the best coverage where people need it. With the big cell towers, for example, we try to cover the entire space. Therefore, they need a lot of energy. If I build up a cell tower, I cover a lot of farm fields, for example. Do I really need to do that? Wouldn't it make more sense if I deploy things like these, where I can know exactly these are the areas where people need coverage, and I focus on those areas and get those right. And in areas where they don't need them, I might still need some coverage for emergencies and whatnot, but I don't need to build out a high-throughput highway to cover these areas, right? Again, something that you learn by looking at what's going on, your experience, all right? So this is one example. Let me give you another example. This is around the impact on the different phone devices and applications have on networks. This is something really interesting. What this shows, this is again from a network from one of our customers. On the x-axis, you have the time of day. So this shows one full day from midnight to midnight. And on the y-axis, you have the signaling load on the network. Signaling load is what you need to establish data connections, to establish communications channels, these kinds of things, right? Signaling. And let's take a look at the red curve here. So what you notice is, if you look carefully here, and your trained eye will immediately see this, there are these peaks. And they are in constant intervals, every 6 hours. Every 6 hours, we notice this peak in signaling load. And peaks is what you're scared of. Traffic spikes is what you're scared of, because they will crash your network. So every time we see something like that, that gets our immediate attention. The problem how this is solved these days is you over-engineer your network. You basically dimension your network to handle those peaks, and then you run idle most of the time. A classical wireless communications network these days runs at 20 to 40% average utilization. More than half of the resources are wasted. So we can eliminate those peaks or handle them differently. That would be very helpful, right? So we then started looking into why these peaks, why these traffic spikes. And this was interesting. It was actually caused by one application that was running on the smartphone, one weather forecast application. It happened that the developer of this weather forecast hadn't really, well, thought it through what impact their implementation design might have, and they simply, without basically ignoring the network, they decided that every 6 hours, their application should check back with a server. Now what happened was, that's fine if you have an application that is used by a few users, right? You don't notice. But what happened here is that this carrier, from which this data is, had rolled out a new, very popular smartphone and had preloaded that application on that smartphone. So now you suddenly had millions of users running that application that had a synchronized signaling event every 6 hours. So different things came together. A popular smartphone was rolled out. The carrier had decided to preload that application, and that application was designed in a way that we had the sync points every 6 hours. That caused a tremendous problem for the carriers because those spikes here were close to the capacity of the network. The lesson learned here, expect the unexpected. This is something you cannot make up. You cannot create in a lab. You cannot predict. You cannot predict that, right? So you have to expect the unexpected. We have to design our networks to deal with things like that in a graceful way. Other example, a couple of them. I go quickly through them. The introduction of new devices, new operating systems, new applications has a tremendous impact on the networks. Tremendous. The average user doesn't realize that. Example, when the iPhone 5, when iOS 5 was introduced, in particular on the iPhone 4, we saw, by monitoring the networks, a 50% increase in signaling as compared to the iOS 4. 50%, more than half in signaling load increase. Why? Because iOS bundled things like iCloud, iMessage, Siri, and so on that are signaling intense. Something the carrier can't control, this carrier does not have control over, but they have to deal with that. Again, expect the unexpected. When the iOS 6 update came along, we can now update the iPhones over the air, OTA update, right? And actually that was used by a lot of people. 10 to 35% of the iPhone users in that carrier's network updated that day using over-the-air updates. That, of course, increased the load on the network tremendously for that day. Again, something that was not available before, they could now update over the air. Before you had to hook it up to your PC, right? And again, significantly impact on the carrier's network. And I have a few more examples here that show that once new hardware is introduced, very often over the same network, it performs better, therefore people consume more data and so on. Again, expect the unexpected. Other example, even if you would know that people now start using smartphones, right? It's hard to predict without knowing which smartphone. So what I show here is for a 3G Android phone and an Apple iPhone, I show the average data subscriber uses per day. And roughly the important thing here is it's roughly the same. So you could say a 3G Android user and an iPhone user consume roughly the same data per day. So you could imagine, okay, it doesn't matter which phone they use. And I design my network based on that. would be a mistake, because once you look at the signaling load that these two phones trigger, you see that there's a difference. The Android 3G phone, while using the same amount of data, actually causes a much higher signaling load on the network, simply how it runs, how the applications are designed, and so on, than the iPhone in that case. So very hard to predict, very hard to predict. Expect the unexpected, right? You can't predict that. So then how do we deal with that? How do we design a communications infrastructure to deal with the unexpected? How do we design communication systems that are able to handle and to deal with these kinds of variances and unexpected things? Well, let's take a look at the web world. The web world has shown us a path how to do that. And the response might not surprise you, because these days, the answer to all problems is not 42 like in the Hitchhiker's Guide of Galaxy, right? The answer to all problems these days is the cloud. So the cloud is something that solves that problem in the web world. And it solves it pretty well. Here's one example. This chart shows on the x-axis here, shows days in the month of April a few years back. And on the y-axis, it shows the number of server instances that a small startup here in the New York area needed to run in order to fulfill their subscriber demands. So what does this startup company do? It's a small startup company, actually now established pretty well. They do something very simple, you might think. They allow you to upload photos, videos, and a music song, and then they create some really cool, impressive videos. So I'm dating myself here, but MTV-style videos, all right? So pretty cool videos. It's hard to describe. When I describe that, it sounds pretty boring. Once you see those videos, you will be impressed. So what do? They take those photos, they take the videos, they take the song, they analyze the rhythm on the song, the beat, they analyze, take a look at the photos, videos, and then they render a very fancy, dynamic, high-quality video on that. So very processing-intensive work. They analyze the media, they render the video in HD quality, so they need a lot of server power. And what you see here is how many servers they needed, how many server instances they needed, all right? And what you see is at the beginning of the month, it started out, well, pretty nice. So they were running about 40 kind of server instances to meet all the user subscribers' demands. But then something in the middle of the month happened. Within only 3 days, the demand for servers went up from about 40 to 5,000. That's, again, expect the unexpected. They needed no longer 40 servers, they needed 5,000 servers to not crash. 5,000 servers I cannot even order and purchase within 3 days. Not even to talk about configuring, testing, system tests, running, deploying it. Not possible. Mission impossible. These guys didn't worry. They probably were, knowing those guys, I know some of them, they were probably celebrating, dancing about their success and didn't have to worry about all of that. Why? Because they don't own those servers. They're using the Amazon EC2 cloud. They are outsourcing that, cloud. Cloud means you decouple the function that you want to provide, the software, from the underlying resource, the underlying hardware. You just rent hardware resources as you need them, and if you no longer need them, you no longer rent them. That's exactly what it did. Once the demand dropped, they just didn't rent it anymore, had no problems. That's a nice model. No upfront cost. No risk. I don't need to purchase huge server farms without knowing that I need them. Only at the point when I need them do I rent them and run my stuff there. If I no longer need them, I no longer pay for them. No upfront investment, no risk. I can easily scale. These guys didn't have to worry at all about, okay, scaling up, scaling down. Very easy, right? So this cloud principle is very attractive so that we can deal with the unexpected. Very attractive. By the way, you might ask what happened here in that mid of month. Basically what it is, they brought a Facebook application out there that included a demo video of their cool stuff. And once people saw what this is about, they all wanted to try it. Again, could you expect that by just putting a demo video out there that you will see from 40 to 5,000? I'm not sure. But no problem if you follow these kind of cloud principles. Now, that got our interest. Our customers, our big carrier customers say, Markus, if you guys can deliver off a network that behaves the same way, where I have no upfront cost, where I can easily scale up and down, that's the holy grail. Can we do that? So we started looking a lot at cloud technologies, right? We started looking a lot at what can we leverage that? Can we build that for our purposes? And the answer is absolutely. We go in these directions. We are cloudifying now the carrier networks and everything, but it is not as easy as one might think. Here's why. Because today's cloud solutions, even the one that I just explained here, they are focused on specific type of applications. The application I described here was basically, here's a bunch of photos, videos, and a song. I hand it over to you, then do your magic, and once you're done, give the result, the video back to me. It's a transaction-oriented application, a batch-oriented application. Here's stuff, here's some data, do it, and when you're done, give it back to me, right? It is stateless, meaning I don't have to remember anything. Here are the photos, videos, and the music. Render the video, then give it back to me, and then you can forget about me. You don't have to remember anything about me. Stateless, all right? And relaxed time constraints. Rendering those videos takes anywhere from 3 minutes to 5 hours with that service, all right? So relaxed time constraints. Now think about if I want to now cloudify, if I want to build a wireless communications network using principles like that, where I separate the function from the underlying resources, I have different kind of applications, not these kinds. I don't have transaction-oriented applications. I have session-oriented applications, meaning that I need to establish a session and maintain state for the duration of the session. Who are the participants in that video call? Are they on hook, off hook? What is their audio quality? How far are they away from the cell station? What is their location? All state information I need to maintain for the duration of the session. I also have much stricter timing constraints. I said before, rendering the video anywhere from 5 minutes to 5 hours. Just to give you one example, in a core component in a wireless network is the mobility management entity. That's the entity who basically has information about where you are as a user. The response time I can afford for getting a response from that entity when I ask, where is Markus right now, tell me where he is 20 to 25 milliseconds. Milliseconds. If I'm not hitting that budget, my call attempt fails. Not acceptable. So we're talking milliseconds as opposed to minutes or hours. Much stricter time constraints. So we then looked at the existing cloud technologies out there and looked at, okay, can we use them for these kinds of environments we're in? And unfortunately, not quite yet. So we can leverage a lot, but we still have some work to do. What I show here are measurements that we took by just reading data from a cloud storage. So why is that interesting? I told you before, we are looking at stateful applications. Applications that need to maintain state. That means I need to store that state somewhere. So I need to write it in the storage and I need to read it. And I told you also in the MME example, I needed to provide the overall response within 20 to 25 milliseconds. That includes reading state. So I asked my team, can you please measure how much time does it take just to read a single state from a cloud storage these days, so we get a feeling. That's what you see here. That's the measurement time, the experiments, and then on the y-axis, we have the response times in milliseconds. So you see it took us on average maybe 200 to 300 milliseconds just to read that information from the cloud storage. Now that's still an order of magnitude above what we need, but to be honest, that would be fine because I think there are hundreds of parameters that you can use to tune and twist actually this system so that I think we could get there by tuning that. So on average, we could get relatively close to what we need. But again, look at these peaks here, these spikes. in quite a few cases, we had access latencies of 1, 2, or 3 seconds. And while in a web world, you might say, if I have to wait for a response for a second in 1% of the cases, that's fine. Nobody cares because you optimize for the average. In our case, that's a killer. Because you all expect from your phone service to have what we call 5 nines reliability. That in 99.999% of the cases, your call gets through. Right, that's a system. And if in 1% of the cases, my access latency is already higher than I can afford, just accessing the information, it's clear this will never work. Right? So there's a lot of work to do. So we are now looking at not about necessarily coming up with something completely new. We always try to see, can we leverage from what has been built already, because that's always an advantage. And we actually our math guys actually come up with some very clever ways on how we can, through statistical multiplexing, we can actually eliminate those peaks here and still use the existing approach. It's a very clever way, something I hadn't thought about before at all. So, but just to show you an example, you cannot just say, let's use all the great cloud technology that we have out here today, and let's just apply it to the communications network infrastructure. It does not work that way. And we know that because we looked at the problem, right? Theme of the talk, look at the problem, we identified that, and then started working around that. This also drives us to a world where I talked about latency, and I talked about some statistical methods. But in general, also what we need to do is we need to be aware that as we move towards the cloud, when we put certain functions on servers and storage devices all over the world, that the communications network that connects those resources becomes very important. Today, the cloud still is pretty much a small number of big data centers, right? And so we can get away with just looking at what is the resource utilization with regard to storage and processing power, for example. We can ignore the network. But in the future, we will move away from a model where the cloud is in a small number of big data centers towards a model where we still have those big data centers, but we have cloud resources all over the world, in central offices, regional offices, in POPs, point of presence, even in users' homes. So we move towards a world where all these cloud resources are much more distributed. And therefore, the network becomes extremely important. So what we need to do, what a lot of our research is about, is now bringing the network aspect into that equation, right? It's not just processing and storage, but it's network as well. And as we do that, it is really important that we do this in an integrated way. Here's one example why. Today, we treat, and that has been a fundamental design issue of the internet, we treat the network as a black box. The application has no idea what the network looks like, has no idea what the condition of the network is. It just says, here's some data, send it from A to B. That's the internet. And that's a good reason, and that's the reason why the internet is so successful, so we need to be very careful with that. For the internet or for the network, the application is a black box. I, as a network, have no idea what bits and bytes are I'm transmitting, right? And I shouldn't. That's a design principle. But this causes problems. This causes problems in the following way. Today, we of course have networks that do engineering. We call it traffic engineering in the network. The networks try, for example, to set up the paths for the data packets so that the load is equally balanced, all right, across the different links. You don't want to have one link loaded heavily and the others is underutilized. You want to equally balance. So we have something we call traffic engineering, where the network provider looks at the bits and bytes coming through and then routes them so that the load is balanced. We call it traffic engineering. At the same time, we now have applications who realize that they need to be smart on how they configure themselves. So some applications, maybe in the video space, for example, they realize they need to minimize the delay so that you have a good experience when doing a video or voice call, right? So they try to configure themselves and try to configure their nodes in a way that they minimize the delay. And now you have a situation where you have two parties competing with each other. You have the network providers who tries to optimize for their goal. You have the application providers trying to optimize for their goal, right? And the result is that we see unstable networks. Here's an experiment that we did that shows on the x-axis, you see TE stands for traffic engineering, OR stands for overlay routing. What that means is whenever there is a TE on this time axis. This means the traffic performed some route adjustments to balance the load. And OR for overlay routing means the application took actions to reduce the latency, to reconfigure itself to do the latency. And on the Y-axis, you see the number of route flaps, meaning the number of routes that changed because of the overlay routing or the traffic engineering. And what you see is that we never reach a stable state. We constantly keep changing the routes in the network. We are oscillating. That's an undesirable state. You want to have a stable state where the routes remain stable. And this is caused because you have overlay routing and traffic engineering ignoring each other and fighting with each other. So when we talked about that one Friday afternoon, actually, I remember that was over a coffee. Coffee is very important in research, and water coolers and everything, right? So over coffee, we're talking about that, and it happened that we had one of our math guys in the room from our math groups. And we talked about that, and then he said, Markus, you know what? This reminds me of a chess game. Actually, let me go to the next chart here. What you describe is basically two parties sitting opposite from each other, and each party tries to achieve its goal, like in a chess game. But the chess players are smarter than you guys. You're actually pretty naive. You just, when you have to take action, you just look at your goal, and you ignore what the other party might be doing. A chess player is smarter. A chess player has his or her goal in the mind, but then tries to anticipate what the other party might be doing next. You take that into account. And that's exactly what we should be doing. When I do some traffic engineering in the network, I should anticipate what the application might do next so that I take that into account, right? And then he basically said, that's a solved problem for us. Just apply game theory, use some of these algorithms, and we did. And the result is here, what you see here. We actually applied these game theories. At the bottom here, what you see is that we still have a learning phase where we observe what the other party is doing and then try to anticipate what it does. And once we learned enough, we reach a stable state where we avoid the route flaps. Just by being a little bit more aware what the application does or what the network does. So a big theme for our research is bridging that gap between applications and network, making networks a little bit more aware of the applications and applications a little bit more aware of the network. Right? This is one big area for us. So let me then wrap up with just a few more forward-looking stuff that's going on, a little bit more crazy stuff, right? Scientists are crazy people in white coats who are in labs and do cool stuff. We do a little bit of that too. And I just want to give you some few examples. One actually that I really liked, which shows also the spirit of Bell Labs, and I think every good research organization is that silent speech here. This was really kind of a side effort. This is not a big breakthrough research that we will announce a product on, but it symbolized a little bit what research is all about. Happened in one, again, a Friday. These Fridays are good, so most of the stuff comes up Fridays. I don't know why. So it was actually Friday evening. I was just on my way out. It was shortly before 7:30. I really wanted to get home. I was walking down the hallway in our building where all the labs are, the doors are open. I was walking down, and then I suddenly smelled a very strong glue smell, very strong, like an industrial glue. And research is always curious, so I followed my nose, right? And I walked into a lab where there was one guy trying to put a wire down his throat. So I said, what are you doing? Oh, I have a microphone at the end of that wire, and I want to see how far down I can still measure ultrasound waves. So I said, okay. Why? Okay, why? He said, oh, that's pretty cool. How much time do you have? I told him, well, if it's interesting, count me in. He said, okay, it's interesting. So I stayed a little bit longer, got in trouble with my family at home, but it was worth it. What he basically was trying to do is, he said, Markus, wouldn't it be cool if I can communicate with somebody around the world without making any noise? Right, that's what he was after. And then the usual example he gives is, see, in a movie theater, isn't it annoying when the person next to you is on the cell phone? Wouldn't it be cool if he or she can talk while making any noises? Honestly, that's not the most convincing use case, but think about the medical use cases. People who can no longer talk, can no longer have voice. think about environments that are extremely noisy. If I could communicate, if I could have a phone call with you without making any audible noise, there's a huge, huge applicability. Then I told him, okay, keep going, what are you doing? And then he said, see, the fundamental idea is, can I inject ultrasonic sound waves that you can't hear into your vocal tract while you speak without making noises, by just moving your lips? And can I then measure the waveform coming back and then reproduce on the other side of the world that sound that you basically would have made? Can I do that? And for that, he said, I need to find out, okay, is it actually stable? Do I get stable waveforms back if I speak, right? How far down does actually my vocal tract reach before the waves come back? And so he did all this kind of work. And I thought that was cool. I had no idea why Alcatel-Lucent as a company would be interested in that, but it was cool. And I immediately realized a lot of digital signal processing will be needed, and probably some artificial intelligence. And this was an optics guy. So I immediately hooked him up the next week with some of my math guys, some of my digital processing guys, and they got together and they worked a little bit on that. And actually, at some point, I had something working where we could not just recognize some of the characters, but even some words, and this is going on now a little bit. So again, something that shows you also, by just being curious, interested, asking the right problem, right? Wouldn't be cool if you can solve that, and then bringing the right people together. Very, very interesting. I talked a lot about communications, about cloud, about processing, and so on, right? So we need to do a lot of this work also because the resources are limited that we have these days. We have limited storage, limited network bandwidth, limited processing power. But wouldn't it be cool if we could basically have unlimited processing power? Wouldn't it be cool if I wouldn't have to worry about having enough computing resources? Well, that's what we're after with the quantum computing, quantum physics. This can be a tremendous game changer, a game changer that we never saw before. Because if we are successful with quantum communications, quantum computing, we suddenly have resources that are basically unlimited from today's perspective. Can also be scary. I use a lot of cloud storage kind of services, but I always encrypt my information, 256-bit AES, because I'm German, right? So I'm a little bit privacy cautious. That seems pretty secure today. If we are successful with that, that's nothing. Can be cracked within seconds. That's a huge game changer. So not to scare you, this is still, I might not even live that, right? And anyway, who would be interested in my photos, right? So nobody. So, but we are looking at, our physics group is looking at the fundamentals of quantum physics with a goal to go towards quantum communication, quantum computing. And they actually were the ones who detected that quantum state, the new quantum state, that we believe will be the foundation for all of quantum computing, quantum physics. So we have some of that work too. Pretty cool, pretty impressive guys. These guys are smart. And then just one last point. I told you a little bit about this one here, where we try to make everything small. But we're also thinking about the opposite, right? So we're also challenging ourselves. So this is really successful. This is the direction we go into. But we're always afraid that we might be missing out if we don't look the other way. So we're also looking at kind of large-scale antenna system. What is that? So MIMO was mentioned before, right? If you have a Wi-Fi access point at your home, it probably has multiple antennas, 2 to 3 to 4 antennas today, right? This is technology that was invented at Bell Labs, by the way. MIMO technology was invented in Bell Labs. What about if I not only have 2 or 4 antennas? What about if I have 100, 1,000, 2,000 antennas in an array? Imagine one of the skyscrapers in New York, the outside being one big antenna array with thousands of antennas, hundreds of antennas. We take a lot of advantage from the 2 or 4 antennas in our Wi-Fi access point. What about if I have hundreds and thousands of antennas, if I could do that? Could we take advantage of that? So again, a lot of math, a lot of interference detection and avoidance going in there, but we are looking also at large-scale antenna systems simply to see if we push in the other directions, what are some of the things that we can be doing. Want to wrap up the talk now, and I want you to remember, I know you always remember only one thing, right? And if there's only one thing that I want you to remember from this talk, it's not just that Bell Labs is a really cool place to work for, but it's the why. In all of the work that you are doing, please do not just ask the how. Do not just ask the what. Start with the why. Why should I work on this? Why would anybody care? Is it really worth my time, my effort to do that? And only once you convince yourself, yes, start looking at what do I need to do to solve the problem and how do I do that. Don't do it the other way around. With that, let me stop here, and then let's see if there are questions, and I will be here for a little bit longer also during the break if you have questions. Thank you.
Yeah, Dr. Hofmann is a great expert in content networking, so I think you don't want to miss the opportunity to ask some questions.
The problem you described with where you had a lot of traffic every 6 hours, this problem can be solved if you include Akamai in the picture, or instead of doing, having the application itself going to the source, to have the source sending the information to the destinations, right?
Is this still on here? Okay. That particular application, these particular peaks were not data traffic, they were signaling traffic. So in that case, a model like we have with Akamai does not help, because Akamai helps basically with the data traffic that we have here. If I have to deal with peaks in the traffic, then a model like what we have in Akamai, where we use caching and content distribution, can help if those peaks are for the same content. Right? If I have a good hit ratio, similarity of the request, then absolutely this helps. And the reason why the internet still and the web still works so well as it does today is exactly for these techniques. But there are now situations where we see these challenges, these peaks, not just coming up in the data path, but increasingly it's shifting the problem to the signaling path. And these are different type of applications where web caching does not really help, because I still need to actually tell where's the user right now, what is the user state, right? I need to find the user kind of stuff. This is something I cannot easily handle with a caching system like what we have with Akamai, for example, right? But you're right that solutions like these help in cases where the peaks are caused by data traffic, and it's caused by requests for similar data that I can cache. But we see increasingly also problems coming up in the signaling path that cannot be handled with these kind of caching schemes.
I really wanted to ask more of a business question in terms of how you see the universities fitting into the innovation ecosystem. A lot has been written how large industrial companies are doing less, basic research themselves, and how do we as the research university fit in with what you've talked about, and how do we better get that information about the what, the so what, who cares aspect of what we need to do to be relevant to industrial partners?
That's a great question. I'm in a little bit of a lucky situation that my parent company, Alcatel-Lucent, has not decided to cut the basic research. They actually continue to invest heavily in Bell Labs. So we, at this point in time, even though we clearly focus more on business relevance, but our basic research is not cut. Having said that, it's very clear that we cannot do it alone. Very clear. We are no longer the size that Bell Labs was 40 years ago. The world is getting complexer, so we realize we need partners. And what we do is we try to partner up with universities where, through the usual programs, internships, master theses, Ph.D s, postdocs, we have profs join us for sabbaticals, these kinds of things. And this is how we try to get in touch with the universities. And when we have students coming in, we try to not just tell them, please do that. Please come in and then implement this code and this feature here. But what we try to do is when a student comes in, typically, and I'm not sure if this is every other place, but typically what we try to do is we let the student first go around a little bit and see what is going on, what is being worked at. Then we work with the student on the why and the what. What is the problem that you want to solve? Why do you want to solve it, right? So we don't present that to the student. We try to teach the student coming in, okay, you have to identify the problem yourself. And we then allow the student to interact with the BDs, Customers, we have to be a little bit careful, of course, but we try to do that, get feedback from customer meetings, and this way we try to get that mindset in. And then we typically do that through the internships or through the program, but what we love most if then a continuation, if it continues somehow, right? We then have a few programs where we also have funding models, even for individual students or for institutions. I have to admit, those budget gets shortened now too. We all know the industry is going through a rough time, but there's a clear realization that we need to do these kinds of things. Also, to be honest, because of the rough times, we could not hire as many people as we need, so we need to bring in fresh ideas. It is absolutely essential that we learn also from universities, academia, what's going on, what is the state of the art of the research, and we try to do that because we cannot hire at the extent we would like to, by bringing more students in, having more dialogue, more interactions. We have some show and tell series where we have a dialogue, so we try to do it that way. So it's not that I can pinpoint to one or two initiatives. It's really the kind of collective things, but I want to be very clear. What you say is extremely important for us as a company as well, because we need to have that tie into the fresh ideas. Let's be honest, I have a lot of gray. I'm getting older too, right? So Kevin laughs about how old my thinking is and what, you still the telephone, right? You don't text and stuff like that, right? So we need to get that fresh blood in. So this is what we try to do that way. I think a continuous dialogue is probably the best we can do at this point.
You better check with the students then first. As part of your presentation, you talked about regular people, students, customers, anyone off the street, being able to use the cloud to save much more information than you could typically in your local hard drive and so forth. I recently saw a commercial for the personal cloud. I forget what the name of it was in the commercial, but it was a little box that you could put in your home. And you could put, according to the commercial, unlimited amounts of data and things on that. And what struck me immediately was, maybe because we were coming to the anniversary of Hurricane Sandy, how would you protect your stuff in the event of a natural disaster?
Yeah. That's something that is really of huge personal interest to me. So I have now 1.3 terabytes of videos and photos of my kids, right? So I love my kids, right? So I have a lot of information. And not just because of Sandy, even before, I'm worried about exactly that. And many of you you probably are because you're tech savvy, but my parents don't realize if they put those photos on the notebook, if the disk crashes, if there's a hurricane, all their lifetime memories are gone. That's huge, right? So to your question, now, first of all, I have also my own little data center at home. So I negotiated a space in the family closet. My wife, after some tough negotiation, gave me a shelf on the top. I put 2 network storage devices up there, a router and a switch, and actually have 1.5 terabyte storage there sitting where I store my personal data. But then I thought about exactly what you said, and basically 2 choices would be. One is that I then have basically a backup server that I use a cloud service provider for. And I actually found one cloud service provider that gives me, for just $3 a month, I store now the 1.3 terabytes also in the cloud. But the key part for me was I can encrypt the data on my client device with my own encryption key. The provider does not have that encryption key. They cannot decrypt their data. So that's what. So there I found one provider who offers that at a very cheap rate and allows me to encrypt it on my side so that I know they cannot snoop into that. But before that, I actually took a different approach. I replicated basically my setup with my parents at home in Germany, and I had an automatic sync going on between my network-attached storage devices. So I had my data in the closet of my parents in Germany and my closet here in New Jersey. And unless a hurricane happens in both at the same time, I should be relatively safe. But it's a really important question, and a lot of people don't realize it, how risky it is to store all that information in just one place that's not secure.
I have one more question over there.
Hi. I'm interested in how Bell Labs balances being research problem-driven versus being consumer-customer problem-driven.
Yes, the question is one that always comes up, and not just being asked, but also what we live, that balance between solving short-term immediate product problems versus keeping an eye on the longer term. And how we solve that is basically, so we separated, first of all, we separated Bell Labs out of the BD organizations, right? So one model would be that you have research embedded in the business divisions, in the business groups. We, on purpose, separated research, Bell Labs, out of the business divisions so that we are not caught into being backwards compatible, solving the burning issues of today, but we can keep a longer eye on. And how that works, actually, I, as a research leader, my job is to tell the CEO of the company and the executive boards and the board of the company how my investment today, how I invest the money given to me, will make sure that the company has what it takes to be successful in 5 years and in 10 years from now. So if I just tell to the executives and to my CEO and to the board, I'm investing the money to solve that problem in 6 months, and when they will ask, so what do you do so that we will be successful in 5 years from now? What are the trends that you expect in 5 years? So for example, the cloud work, to be honest, started 8 years ago. 8 years ago, we realized that this is a did we know what exactly it will look like? No, but we just sensed that's the way the future will be. So 8 years ago, I invested in cloud work, right? And I had to explain to my management why I'm doing that, and I had to explain it that way. Then at the same time, we set basically the north, the longer term goal, this north, this is where we want to go. Then at the same time, I need to explain the first 1, 2, 3, 4 steps we take now during the next 6 months to go towards north. So this is how we balance it. We set the goal out a couple of years. It's always cliche to set 5, 10 years, whatever it is. We set it out a couple of years out. This is north. We then look at why we need to make a case. And then that's what I'm asked for to provide. And then at the same time, I'm being asked, so now tell me the first 1, 2, 3 steps you will take over the next 6, 8 months to move towards that goal. This is a little bit how we try to balance that. Now, to be honest, there are also cases where sometimes we are engaged in fire drills, like if there's a big customer problem and we have just built up the expertise in research to quickly help, we go in there and help as well, right? We also have these kind of short-term engagements. This helps the company, hopefully, but it also gives us insights. That's the two-way, right? Because we come out of these engagements having learned a lot about how the networks run today, what the problems are, and very often do we then identify those problems I was talked about for the longer term. So it's not a very easy answer, but I hope I was able to give you some feeling.
Yeah, so I think that's all for today's keynote speech. I would like to thank Dr. Hofmann for being here, for giving us such an inspiring talk, and I personally learned a lot from it. I hope you do. In order to present our appreciation, we'll have a special gift for you.